Hello, and welcome to a lecture on frequency conversion. I'm Steve Ellingson. Here's an overview of this lecture. First, we'll explain why we bother with frequency conversion. Why is it important in receivers and transmitters? We'll talk about frequency conversion using multiplication, which is the primary method for doing it. We'll talk about down conversion, which is the process of reducing frequency. And we'll talk about the two basic methods for doing that, those being low side and high side injection. And I'll show you examples. We'll talk about up conversion, which is the process of increasing frequency. And again, we'll have low side and high side injection versions of that operation. And then finally, I'll talk about the image problem. So first, why frequency conversion? Typically, it's not practical to process signals in the same frequency band in which they are transmitted or received. You've already seen examples of how things get more difficult as frequencies increased. It gets harder to obtain the desired values of capacitance and inductance. It becomes harder to do frequency synthesis, and so on. So in a receiver, we will typically do frequency conversion, and the stage that processes the lower frequency will be referred to as an intermediate frequency stage, and the intermediate frequency is the center frequency at which that stage operates. And I should also point out here that the lowest and final intermediate frequency in a receiver is sometimes referred to as a baseband. Baseband has many meanings in RF and digital systems engineering, so you have to be a little bit careful. But in the context of frequency conversion, the baseband stage is normally the one which is at the lowest frequency, the first one in a transmitter or the last one in a receiver. So receivers in particular, I should say one more thing. It's typically not practical to apply sufficient gain without taking advantage of the isolation that comes from the use of intermediate frequencies. Now, what do I mean by that? We'll see in a later lecture, when we talk about receiver design, that the total gain in a receiver is typically somewhere in the ballpark of 50 to 100 dB. That's what it takes to get the signal from the level at which it's received to a level at which we can successfully digitize it or demodulate it. Now, we know from amplifier design that a single amplifier stage is usually somewhere between 10 or 15 dB. So we can see right away that we need a string of amplifiers to achieve this kind of gain, 50 to 100 dB. Well, if we have a string of amplifiers, each one of them consisting of a bunch of transistors, then we have the increased possibility of feedback. So we have some possibility of signals going from here to here, for example, or from here to here, or from here all the way back to the beginning. We know this because we saw how much difficulty we were having keeping RF out of the power supply when we talked about amplifier design. So you can anticipate when we have lots of gain, strings of amplifiers, it becomes very difficult to provide sufficient isolation from stage to stage. So the concept becomes, instead of piling on amplifier after amplifier in one stage, do a frequency conversion. And now the frequency which emerges here is different from the frequency which is going in here, and they're less likely to interact in a bad way. So an intermediate frequency is a way to provide isolation and to a large extent mitigate the possibility of instability because feedback through paths such as the power supply. Typical receivers have on the order of 1 or 2, sometimes 3 intermediate frequencies. There is a class of receivers known as tuned RF receivers which have no IF. That's a somewhat different category. We'll talk about that when we talk about receiver design. So here's a recipe for frequency conversion. And I note here it's incomplete. We're going to have to add one more detail. We'll talk about that at the very end of the lecture. But the idea is that we have some signal at a center frequency of omega sub I, and we have a mixer. A mixer is simply, for our purposes, a multiplier. So we're going to assume that this thing we're calling a mixer is simply a device which can multiply two inputs. And the other input is the local oscillator signal, and the local oscillator signal is centered at omega sub L. And when we multiply those two together, we have one additional step, and that's to reject the undesired multiplication product. you may already be able to anticipate, and I'll show you in just a moment, that when you multiply two narrowband signals together, you get signals at the sum and difference frequencies. And we'll see that's the case. So to demonstrate that, here's the simplest input signal I can imagine. A sinusoid, A cosine omega sub I being the input frequency, times t multiplied by A, the magnitude. The LO, cosine omega sub LT, and when we multiply those two things together, we get AB cosine omega IT cosine omega LT, which by applying the relevant trigonometric identity, we get two terms, one being cosine of the sum of frequencies, cosine of the difference of the frequencies. And then finally we apply a filter, normally either low pass or high pass, whichever one is required to eliminate whichever of these two we do not want. So we keep one, we try to reject the other one. So first, down conversion by low side injection. So now we're talking about reducing frequency. We're going to do it in a particular way. Low side injection means that the LO frequency is less than the input frequency. When that's the case, then this is the term that we're going to want to keep, because this will give us the output frequency that we want. We'll discard this term, and we'll use a low pass filter to do that. The other approach to down conversion is high side injection. In high side injection, the LO frequency is above the input frequency. So in this case, we're going to discard this particular product. We're going to do that using a low pass filter. And we're going to keep this part. Now you'll notice a difference happens here. You'll notice that if you actually work through this, you find that the frequency is actually minus omega naught. Minus omega naught, not plus omega naught. Now does that make a difference? Well, it does. What it means is that we have spectral inversion. Let me explain what that means for just a moment here. If I have a chunk of spectrum that's like this, and let's say this is 0, low side injection would have given me a chunk of spectrum which goes right there. But when I use high side injection, what I'm actually doing is I am shifting this thing down here. And since it's there, it looks like this, but this is really this in the real spectrum. So I have a spectral reversal. When I see negative frequencies, that means that the spectrum of the signal that I'm operating on is going to be spectrally reversed. Now the consequences of spectral inversion depend on the modulation. AM, FM, these modulations could care less because they have symmetric spectrum. Single sideband might matter, depends on how you demodulate it. But for something like BPSK, QPSK, QAM, all these modern modulations, they do not like that. So you can use this technique to down-convert signals to having those modulations, but you must do something to account for the fact that it's been spectrally inverted by this particular choice of high side injection. So you might ask, well, why bother doing high side injection if we have this possible problem? Well, high side injection puts the local oscillator frequency and the undesired products at higher frequencies, which makes them easier to filter out using a low pass filter. Filtering of spurious and undesired products is one of the big headaches in receiver and transmitter design. So if we can come up with ways that reduces this burden, even if it creates a little bit of a kink here, we're happy to find ways that we can rectify that if we can improve the situation here. So let me show you an example here. In this example, we have an input signal at 150 megahertz. This particular signal has a bandwidth of 30 kilohertz. So this could be a very, very typical land mobile radio communication signal, for example. And we want the output to be 10.7 megahertz. And the question is, what should the LO be? What should the low pass cutoff frequency be? Well, if we use low side injection, LSI, low side injection, the LO frequency should be the difference of the input frequency and the output frequency, which here is 139.3 megahertz. The undesired product will be the other one of the two products that this mixer generates, and that's at the sum of the input and LO frequencies, which is 289.3 megahertz. So here, for this filter, we're going to want something that cuts off at a frequency which is above 10.715 megahertz. That's this center frequency plus 15 kilohertz, which is half the bandwidth. And we're going to want that cutoff frequency to be below 139.3 megahertz. Why is that? Well, because we just decided that this is going to be 139.3 megahertz, and some of this will almost certainly leak through. We'll say more about that when we talk about mixers, real mixers. Ideal multipliers, we're not going to have to worry about this, but for real mixers that try to implement this multiplication, some part of this is going to leak through, and we'd like to get rid of that. So the low pass cutoff frequency for this filter should be somewhere in this range, 10.715 to 139.3. For high side injection, we want the LO frequency to be the sum of the input frequency and the output frequency. Here that's 160.7 megahertz. The undesired product will be, again, the sum of the input frequency and the LO frequency, which is 310.7 megahertz. And therefore the low pass cutoff frequency should be somewhere between 10.715 megahertz, just like before, and below 160.7 megahertz, again, because that gives us the opportunity to suppress this LO bleed through to the extent that we get it. For the high side injection approach, this one right here, the output will be spectrally flipped. So if we're using a modulation that has asymmetric spectrum, we're going to have to keep that in mind. Now, up conversion. Again, for up conversion, we have two options, low side and high side. For low side up conversion, the LO frequency will be the difference between the output frequency and the input frequency. We're going to keep the sum term, and we're going to discard the difference term using a high pass filter. For high side injection, the LO frequency will be the sum of the output and input frequencies. We're going to discard the sum frequency, and we're going to keep the difference frequency. Now, again, note that this difference frequency results in a signal which is centered at minus omega naught, so we see once again we will have spectral inversion. Again, the consequences of spectral inversion depend on the modulation in exactly the same ways I just talked about for down conversion. But again, we're interested in high side injection because it puts the LO and the undesired product at the higher frequency. So we require a low pass filter instead of a high pass filter. So here's an example of up conversion, basically the up conversion version of the down conversion example I just showed you. So here we're going from 10.7 megahertz with a 30 kilohertz bandwidth. We want to upconvert it to 150 megahertz. So again, the symmetrical version of the down conversion example I just showed. We'd like to know what to choose for an LO frequency. Should this filter be low pass or high pass, and what should the cutoff frequency be? Well, if we're doing low side injection, the LO frequency should be the difference between 150 and 10.7 megahertz, which is 139.3 megahertz, which should sound very familiar because that's what we found for down conversion. The undesired product is centered at the difference between the input and LO frequencies. Now that's a negative frequency, but we know that that corresponds to a positive frequency, and that's going to be 128.6 megahertz, and that's going to be spectrally reversed. We don't care here because that's the undesired product. So what we want here is a high pass filter, and it should have a cutoff somewhere above the LO frequency and below the bottom edge of the modulation at the output frequency. For high side injection, the LO should be the sum of the output and input frequencies. That's 160.7 megahertz. Again, that should sound familiar. The undesired product here is going to be centered at the sum of the input and LO frequencies, which is 171.4 megahertz. So here we're going to want a low pass filter with a cutoff above the high edge of the modulation and below the LO frequency. And in this case, the desired output will be spectrally reversed. So one more issue to consider here, and to consider this we'll return to the down conversion example. Down conversion from 150 megahertz to 10.7 megahertz. And we found that if we were going to do that by low side injection, the frequency for the LO would be 139.3 megahertz, and the filter would be low pass with a cutoff somewhere between 10.715 and 139.3. Now, here's what I want you to consider. What happens if there is some other signal in the environment here that has a frequency of 128.6 megahertz? Well, 128.6 megahertz plus 139.3 megahertz is not going to be a problem to us. However, 128.6 megahertz minus 139.3 megahertz is minus 10.7 megahertz. Well, we know that that's plus 10.7 megahertz spectrally flipped. But wait a minute, that's where our desired signal is going to go. So what we found here is that there is some other frequency which ends up at the same output frequency as our desired signal. So we call a frequency that has this property an image frequency. It's a non-desired frequency which ends up being translated to the same frequency as our desired signal. Another way of saying this is that an image frequency is an undesired input frequency which maps to the desired output frequency. Note that there's nothing you can do at the output to remove this interfering signal. In other words, once I do the mixing, there's no way I can separate these two signals. Therefore, if I'm going to deal with this possibility, if this possibility exists, I must deal with it before it gets to the mixer. So here's the complete recipe for frequency conversion, accounting for the possibility of an image frequency. I have still a mixer. I have an LO, and I might be doing low side or high side injection. I have this issue of dealing with undesired and spurious products, the undesired multiplication product, and LO bleed through. But now I also have to consider rejection of the image frequency. So those are the three parts that you always have to consider when you do frequency conversion of this type. That completes this lecture on frequency conversion.